So you have seen now how have we built a classification model, how have we calculated the error, what was the problem in the basic model, how did we overcome linearity which was an issue, how did we build a more complex model by adding non-linearity and by embedding a large number of layers into your neural network in order to get the classification done. Okay, so these are all the steps of building a particular neural network. Here we have taken example of a classification. So in this you are seeing actually how to build an artificial neural network. Now once you have calculated, once you have built your model, the next step will be to choose for an optimization method. So as I told you, when you bring in non-linearity and when you interconnect a number of layers together, you are actually solving a lot of problem which was further not being solved when you have used linear model. So coming to the method of optimization, things will be pretty much simpler now. So when you check optimization, now you can use a method which is similar to your linear regression to solve classification also. Now if it was a single layer network, then what you would do? You would directly derive the partial derivative. What was it? You would directly calculate, if it was a single layer, mind it again I am telling, if it is a single layer, then you can directly derive the partial derivatives of what? Dou L by dou W. L is what? Your mean squared error. Okay, we have been discussing this later, right? So now you have got two parameters that you are working here, one is weight and one is bias. So you will take up your loss function L and you will calculate the partial derivative. Why partial derivative? Because we have two parameters. Had it been a single derivative, then you had it been only one parameter, then you will write dl by d theta if theta is the parameter, for an example. But then since here you have two parameters, so I am using partial derivative. Okay, so when I am using partial derivative, I will write dou. Okay, when I have a single variable where it is dependent on, I will write d. I have two now, so I am going for partial derivative. So I have dou L by dou W and dou L by dou B, because I have weight as well as bias which is playing their role in calculating your loss function. So dou L by dou W, dou L by dou B, you will be calculating the partial derivative very much directly, and then you will calculate gradient for every step. That is, you apply a gradient descent algorithm. You calculate gradient for every step and then you update the parameters. You all remember that formula, right? If you want to update it, say weight, then if you are talking, say new weight is equal to old weight minus eta and nabla, and then you have E. Okay, gradient of your error or your loss function, and then you have your learning rate fixed, then you subtract it from the old weight and then you calculate new weight. So it all depends with your different types of parameters that you are following. So you are applying gradient descent algorithm very simply to it. Now what is the problem now? The problem is the complex nonlinear functions have been embedded now. The number of the network layers is increased and the length of the data features, that is your data set that you are dealing with, is also increased. Alright. Now what happened with that? The model became very complicated. So now also if you want, you can actually apply that gradient descent algorithm, you can apply mean squared error, you can do those things, but doing all those things manually is a very cumbersome task. It is very hectic. Okay, so the model becomes very complicated. It is difficult to manually derive the gradient expressions. Once the network structure changes, the model function and the corresponding gradient expressions also change. So you have each and every pros and cons which is listed over here. What happens if you really want to apply gradient descent manually, layer by layer, doing everything by yourself? But if I see, with so much increase in the size of the network and so many parameters available, manual doing this is not possible. Like I discussed, had it been a single layer or if in case two layer, manual calculation is very easy. But when your network becomes more and more complicated, manual calculation is not at all feasible. Then what should we do? So now you have to think, what is the solution that might have happened by which it is possible today to build such a complicated network. Just think about it for a minute. What should be done now? the model was suitably built so that you can actually calculate and apply gradient descent fine. But then now how? Because doing manually things didn't work. So what to do now? So the solution was building deep learning frameworks. That's why here from now onwards you will be learning what is TensorFlow. Deep learning frameworks, I gave you entire list where to use what, but I told you we have got TensorFlow in our syllabus. Why? That is this reason. So invention of deep learning frameworks was the solution to this particular problem, because it was possible to calculate differentiation, that is gradients, automatically using this particular technology. So lot of mathematical functions and their solutions, the answers became very fast and very simple to do. So with the help of auto differentiation technology, deep learning frameworks can build neural networks, computational graphs during the calculation of each layer output, corresponding loss functions, and then automatically they would calculate the gradient, which is dou L by dou theta. Theta could be any number of parameters, like it can be n number of parameters for n number of layers. So it made user's task or model builder's task very easy. So what will be the users doing? The users will only be setting up the network. I want so and so number of inputs of neurons. I want so and so hidden layers. This is going to be my nonlinearity function, that is my activation function. I am going to use so many number of neurons in my hidden layers. I am going to use so many number of neurons in my output layer. That's it. Internal calculations of your gradient with respect to all its parameters of weights and biases, you have to just leave it. That burden is gone. It is completely taken care by deep learning frameworks like TensorFlow. Okay. So users only need to set up network structure and the gradient will be automatically calculated and updated, which is very convenient and efficient to use. So by this we have come to know that not only building a model was different in classification, you encountered several issues which you tried to solve. Then you wanted to have an optimization method which is possible manually, but then as your situation got complicated, it was difficult. So you got to know that if you really want to dive into deep neural networks and actually work with them, the first thing that you would require is to learn these deep learning frameworks properly, which is TensorFlow deep learning framework and Keras API. So in the next unit, we are going to discuss thoroughly upon TensorFlow and Keras. We are trying to grab hold of it, and post that you will actually see the magic of deep neural networks like CNNs and RNNs, and that is going to be wonderful. Now in my next topic, there is going to be a hands-on session on classification. I would like you to pick up like I have picked up the same data set that I have been discussing so far, the handwritten data set, and I already discussed what all went through the steps involved in building that particular model, but I leave it on you. You can pick up any data set of your choice and perform the same steps or a little bit different steps, but same strategy, and you could develop your own classification model. So the next class is going to be a hands-on on classification. Post that we are going to see our second unit, which deals with deep learning framework of TensorFlow and Keras API.